So I'm glad to see we have the beginnings of a new presentation up behind you. Let me tell you a little bit about our next speaker. This person I have met several times doing these sort of things. She is now touring the world, but particularly this country, but she'll go anywhere she gets an invite to talk about maths and science. She has made a particularly big headline splash, reminding people that even scientists have emotions. It turns out this is quite an important fact to realise that people who do science are human beings, so she's going to tell you more about that. I can tell you some other things about her. She is regularly on the TV. You may have seen or heard of a programme called Why Do Ducks Quacks? Remind me? Something about ducks and echoes. Ducks, quacks, don't echo. If you want to know why, there's your question for later on. I'm sure she can answer that in about half an hour instead of 30 seconds. She has also written books. She has a PhD in cancer research. She is a trained actress and a singer. She is going to talk to you about lies, damned lies, and newspapers. Please put your hands together for Emily Grossman.
Thank you, Ben. Good morning, everyone. How are you doing? Anyone seen Duck Quacks Don't Echo? Awesome! That's what happens when you're on a really successful show on Sky. Nobody watches it. Anyway, so I'm here... Uh-oh. We have a problem. My clicker doesn't stretch. Why is it not working? We had this last time. Yeah, it should be working. Okay, I'm going to have to... Yeah, change clicker. Change clicker. Quick, quick, quick. Yeah, but we need to go there. Okay, so chocolate accelerates weight loss. Basically, chocolate makes you lose weight. Reckon that's true? Well, it must be true, right? It's in the Express. It's in the papers. The question is, can we believe everything that we read in the papers? No. Hands up if you think that chocolate actually makes you lose weight. So, this is, I dare say, slightly ridiculous idea. And you would be forgiven for thinking, well, it must be true, it's in the newspapers. But the point is, we cannot believe everything we read in the newspapers. This was a study that was actually done as a scientific study, but it was created by a journalist with the sole intention of seeing if he could do pretty rubbish science and get it in the newspapers as long as it basically told a good story. He did an experiment. He used 5 people in his experiment. If anyone knows anything about statistics, we call this a sample size of 5. It's not very rigorous, shall we say. He used 5 people in the experiment. He didn't use what we call adequate controls, which basically means that he gave some of the people some chocolate, he gave some of the people a drink of water, and then he weighed them. And well, of course, people who drank lots of water are going to be a bit heavier. And of course, the people who drank the chocolate, who ate the chocolate, weren't actually much heavier, and so it looked like they lost weight. Plus, the actual amount of weight that these people supposedly lost after eating chocolate, remember there's only 5 of them anyway, was a tiny, tiny amount, what we call statistically insignificant. So, moral of this story is that there are people out there doing experiments and putting stuff in the papers that are not necessarily completely accurate and true, not even deliberately, but we've got to be careful, because as long as it tells a good story, there's a good chance that it could end up being in quite a reputable paper or journal. So, in my, not that the Daily Express is quite reputable, but I will come on to other examples of where they are. Now, in my line of work, as Ben said, I'm a science communicator, which basically means I get to talk about maths and science on the TV, on the radio. I go into schools, primary schools, secondary schools, universities, science events, science museums, and I give talks about maths and science. And I write books and articles about science. And as part of that work, I often get called upon by TV shows or by news programs to comment on stories that have been in the newspapers about science. And these stories often include numbers. They include studies which involve statistics. And I often have a short amount of time to read these stories and to work out, is this true? And in which case, how can I explain this on a TV show or on a news program so that other people can make sense of these stories? Which means there have been times in my career where I, too, have been caught out by things that have been in the papers which are not necessarily true. So, to illustrate this, I'm going to do something slightly crazy, maybe slightly bold, slightly brave, which is that I'm going to tell you about 3 of the most embarrassing moments of my career to date. There's probably going to be more. Hopefully I've learnt by each one, and hopefully you will learn by me showing you each one. Now, embarrassing moment number 1. So embarrassing moment number 1 is I'm going to show you a clip from a very early series of Duck Quacks Don't Echo. If anyone follows the show, we've done 6 series now, but this is from series 1, I believe it was. And I'm going to show you a brief clip of me explaining a science fact. While you're watching it, I want you to be having a think. Why do you think this was a particularly embarrassing moment for me? And then when it's finished, I'm going to give you 30 seconds to turn to a friend and discuss it. Okay, so hopefully the sound's working. Have we got sound plugged in? Brilliant. Okay.
Clever clod boffins to help us get to the bottom of the fact. So please welcome rocket scientist Dr Simon Foster, expert in cell biology and genetics Dr Emily Grossman, and chemical engineer David Wharton, otherwise known as the Verifiers. So come on, is there any truth in Simon's fact?
Well, actually about 10% of the population, including me, are left-handed. And unbelievably, a study has shown that in left-handed people, they are on average going to live 9 years less than right-handed people. So it is actually true. Studies have shown that left-handed people are nearly 6 times more likely to be involved in life-threatening accidents. So maybe it's just that we're more clumsy, or probably that we're facing the perils of living in a right-handed world, where for us everything is upside down and back to front. So for example, the safety switches on most machines are on the right-hand side. But it's not all bad news, because left-handed people, on average, tend to be a bit more creative. They make good mathematicians and musicians, and sometimes they make great athletes because the reaction time for the left hand is marginally faster than for the right hand. That's incredible. I never knew that.
Okay, everyone. So turn to someone sitting next to you. You've got 30 seconds. Why do you think that was a particularly embarrassing moment for me in my career? Okay, any thoughts? Hands up. Anyone got any suggestions? Yes. Between? There's no correlation between the points I made. You mean in terms of which bit? Any of it. So it was all rubbish. Maybe. It probably actually was. The point is, I did get it from somewhere. I didn't just make it up. In fact, I actually got it from a newspaper article in the New York Times, which is a pretty reputable newspaper. It's not like the Express. For the New York Times, we could probably believe what they say in there, and in fact, it quoted a study in the New England Journal of Medicine. Now, admittedly, this was a long time ago, 1991, but that shouldn't make any difference. The New England Journal of Medicine is a highly reputable journal, so there's no reason why this shouldn't be true. And they said they studied 1,000 Southern Californians. That's a huge sample size, 1,000 people. It's pretty good. And they said that right-handers on average lived to be 75 years old, and left-handers typically died at the age of 66. Now, this is what's called a death cohort study. A death cohort study means that you study the death records of people who've recently passed away. And what they did is they studied the death records of 75-year-olds, the death records of 66-year-olds, and they found that the number of left-handed people in the population of 75-year-olds who'd recently deceased was much lower than that of the 66-year-olds, and therefore concluded that being left-handed must therefore make you die younger. Can anyone now see where we're going with this? Anyone see a problem? Yes. Left-handedness?
More people are left-handed in recent years.
Nice. Did you hear what he said? More people are left-handed in recent years. Why? What do you mean by that?
I mean, the people who were born, say, 66 years ago were more likely to be left-handed.
Why? Why were they more likely to be born left-handed than the ones who are older?
I'm not sure why. But,
Okay, great. Can anyone elaborate on this? Yes. Nice, spot on, excellent. So it used to be forced in schools, if you were born left-handed, for you to actually try to write with your right hand. The word sinistra in Latin means left, and it's been turned into sinister, bad, wrong. It was stigmatized to be left-handed. Hands up here who's left-handed. Okay, it's about 10%. If we were sitting here 100 years ago, how many of you do you think would put your hands up for being left-handed? Very, very few. There's a graph here from a book called Right Hand, Left Hand, which actually shows 100 years ago it was probably around 3%. Not because fewer left-handers were born left-handed, but because, exactly as you said, there was a stigma, people were forced to write with their right hand because it was thought as bad and wrong. Also, in the days where people wrote with pen and ink, if you wrote left-handed, you would smudge the ink, and later on, if you went to work in factories, like I said in the clip, you would end up basically in a disadvantage because all the machinery was designed for right-handed people. Now, what this means, fundamentally, is that what I verified on the program, I said left-handed people die 9 years younger than right-handed people, based on a study which was to do with this death cohort study. Now, this death cohort study is fundamentally flawed for this reason. Because if it's kind of like saying, okay, so the 75-year-olds, there were fewer left-handers. The 66-year-olds, there were more left-handers. We have therefore concluded that being left-handed makes you die young, as opposed to the fact that there are simply fewer left-handers in the older population because it was stigmatized. It's kind of like going into an old people's home and asking how many of them use Instagram. If I asked you how many of you use Instagram, how many of you? Probably about 90%. If I asked old people's home how many of them use Instagram, how many do you reckon you'd get? About 2%. Would you therefore conclude that using Instagram has made people die younger? That's why there are fewer of them in the older population. No, there simply are far fewer people using Instagram in the older population, like there are far fewer left-handers in the population of 75-year-olds than there are in the population of 66-year-olds. Does that make sense? Any questions? Because this is quite a tricky concept. Because if you were to believe that actually being left-handed made you die younger, 9 years younger, that's a huge increase in risk. That's basically saying that being left-handed is the equivalent of smoking 100 cigarettes a day in terms of the reduction in your life expectancy. That doesn't make sense. So why would myself and people like that have to claim that it's true? It's because these death cohort studies are very, very commonly catch people out. They even catch out the experts. It took until 2013 for the BBC to write a report on this on their website to say, watch out, this is not actually true. You're going to find this study all over the internet. You'll find it on BuzzFeed. You still will if you put in left-handers die younger. It's still out there. But actually, it's not true. Now, death cohort studies trick even the experts. They tricked me, and I'm not a statistician, but they certainly trick people who've written books about this stuff. And it's not the only one. This left-handed one is not the only one. There was another study that was actually published in the British Medical Journal, which is a highly reputable journal. And this was published to say that anaesthetists die younger than other medical professionals. There was a death cohort study to say that the average age of death of anaesthetists was younger than those of like surgeons or paediatricians or whatever it might be. Therefore, being an anaesthetist makes you die younger. No. It's another case where actually anaesthetists just are younger because anaesthetism is a relatively young form of medical specialism. Therefore, people who are anaesthetists tend to be younger. Similarly, a study was carried out in The Lancet, another reputable journal, which looked at the death records of female versus male doctors and said that women doctors die younger, probably due to the stress of being female in a male profession. Again, no, that's not true. It's simply that female doctors are younger because they've been coming into medical professions more recently in recent years, just like we've got more left-handed people now than we used to. Make sense? Any questions? Because that's quite a tricky one. So the golden rule from this is look out for the unintentional misuse of statistics, such as death cohort studies. Be very careful with things where a characteristic has actually changed over the years, like being left-handed or being a female doctor, because it will trick even the experts. Okay, embarrassing moment number 2. Embarrassing moment number 2 was when I was called upon by a TV show called ITV's This Morning. You've probably never watched it because it's on in the mornings when you guys are at school. But it's a kind of chat show. It takes a look at what's going on in the news. And I was phoned by them the night before and said, can you come on the show tomorrow morning to talk about this story that's hit the headlines today? So this was in 2014. Black mum gives birth to a white baby. Anyone remember this story? It also kind of trended on either Facebook or something for a while, because it was this like really interesting story of a black woman with a white husband, but had a perfectly white baby, a totally white baby. Now this is obviously very, very unusual. And in the newspapers it said 1,000,000 to 1 odds, 1,000,000 to 1 odds that baffled midwives. Now, This Morning called me up and said, you're an expert in genetics. Oh, I should add, by the way, as a science communicator, if any of you are interested in this as a profession, I now get, yes, my PhD is in cancer research, but I now get called upon to talk about all sorts of different things. I did a story on the Sky News about the odds of winning the national lottery and the statistics of how likely it is you will win. So I get called upon to talk about all sorts of different things. And as a science communicator, my job is to research it very quickly, find out as much as I can about it, and see if I can then explain it in a way that helps others to make sense of it. So I thought, okay, I don't know much about inheritance of skin colour, but to me this seems like a pretty weird idea that you could have, again, like we said in the chocolate study, this is a sample size of 1 this time. As far as I could find out, nobody had done any genetic testing on the baby or the mother, and they were claiming this 1,000,000 to 1 figure, and as far as I could find out, there was no evidence anywhere, there was no information anywhere about where they got this number from. Where did they get this 1,000,000 to 1 figure from? I thought, okay, maybe some doctors told them in the hospital, but I couldn't find any reports of it anywhere, and there was no more information. They hadn't genetically profiled the child or the mother, and they didn't have any more children for her to compare against. So I thought, okay, this is really tricky. This could be a case of whether newspapers are just plucking a random number out of the air, but I have to base this on the fact that they must have got this from somewhere, but I have no idea where. So, this is what I chose to do.
She's handed her baby, a newborn baby, who's a wee bit surprised because it may not escape her attention there. Catherine is black, of Nigerian heritage, and there is a little man on the knee, Jonah there, who's white. Okay, her husband Richard is white, but this shouldn't really be, because we've got genetic expert Dr Emily Grossman here as well, and this would be what, how uncommon would this be?
Well, the doctors that spoke to this amazing situation said that it was a 1 in a million chance. Now, there is one explanation that could explain why that would be. If we...
What I stopped it on purpose. What I chose to do is to try to give them an explanation that would fit those odds, knowing full well that there may be other explanations that were possible, but knowing that they were not going to accept me simply saying, oh, well, we don't know. So my choice was to say, can I do some kind of forensics on this? Can I kind of do some backwards logic to go from the answer, if we're trying to get a 1 in a million odds, backwards to what logical process in terms of genetics could have led to a 1 in a million odds, and then explain to them, but actually we don't really know, short of her having another 10 or 100 babies and doing some statistical analysis on it and trying to work out what's going on by doing genetic testing, we don't really actually know. So, this is what I decided to do, and I'm going to get you guys to help me with this in just a moment. Knowing a little bit about genetics, which hopefully you guys do too, I'm sure most of you are doing GCSE biology. Everyone doing GCSE biology? You might have learned a little bit about genetics. If you haven't, don't worry, because I'm going to take you through it. But I thought, okay, how can we try and figure out the odds of a black woman having a white baby? Let's imagine a very simplistic situation, which is clearly far too simple, but just let's build up a sort of model, because as mathematicians, that's sometimes what we do. We build up a sort of paradigm or hypothesis or a model that we can then extend and extrapolate to build up to a more complex situation. So I said, okay, I know a little bit about genetics. Let's imagine that this mother has, well, we know that every person has 46 chromosomes arranged into 23 pairs. Of the 23 pairs, each person will have inherited one from their pair of each pair from their mother and one of each pair from their father. So let's imagine, first of all, that this is a pair of chromosomes in the black mother. And on that pair of chromosomes, there is a gene that represents skin colour. Now, obviously, it's more complex than this. There's many genes, but let's just start with one for now. So let's imagine there's a gene that represents skin colour, and she has inherited, either from her mother or her father, one white version of the gene and one non-white, which I've coloured in green, version of the gene. So somewhere in her family history, there was a white ancestor, perhaps, which meant that she has carried down from her family tree a white version of this skin colour gene. By the way, what do we call a version of a gene? An allele. Excellent, well done. So, if this were the case, and it was this simple, which it's clearly not, when she creates an egg cell, which will then go on to be fertilised by a sperm and make a baby, she will take either one or other of this pair of chromosomes into the egg cell, either the white version or the non-white version, giving two options for egg cells, 1, 2, one of which would carry the white version, and if it were this simple, that would mean that she would have a 1 in 2 chance of passing on the white version to her baby, giving a 1 in 2 chance of having a white baby. Obviously, it's not that simple, because that would mean that any black woman who had a white ancestor somewhere in her family line would have a 50-50 chance of having a white baby. Clearly, that's not true. Clearly, we don't see that all the time. Do you get my logic? Any questions? So I then went on to say, okay, it's clearly more complex than this. What if there were 2 chromosomes, and she had a white and a non-white version on each of those 2 chromosomes? If we separate them into egg cells, we have the white and the non-white version of the blue chromosome, we have the white version of the orange with each, or we have the non-white version of the orange chromosome with each, giving 2 times 2 or 2 to the 2 or 4 options this time, one of which would involve passing on to baby Jonah both white versions of both genes and therefore potentially making a white baby. This would give a 1 in 4 chance of having a white baby. Again, clearly it's more complex than that because not all black women have a 1 in 4 chance of having a white baby if they've got a white ancestor. So I thought, okay, what if there are 3 chromosomes involved and 3 different genes? What would be the odds of passing on all 3 white versions? So we've got the blue, the orange, and the purple chromosomes this time. We've got 2 times 2 times 2, or 2 to the power of 3, because there's 3 different chromosome colours this time. Therefore, 8 options, one of which would involve passing on all white versions, white alleles, giving a 1 in 8 chance of having a white baby. See where I'm going with this? Where I'm trying to get to, this time with 4 chromosomes, with 4 different versions of the white allele, this time 2 times 2 times 2, or 2 to the power of 4, which would give 16 options, one of which would be all white versions going to baby Jonah, giving a 1 in 16 chance of having a white baby. Where I'm going with this is, what can we do, therefore, to scale this up? How many genes would there have to be on how many different chromosomes if we follow through this logic in order to get to a 1 in a million chance of passing on all of those white versions to the baby and having a white baby? In other words, 2 to the power of what would give us a 1 in a million chance of passing on all those versions to the egg and therefore making a white baby? That is the question that I asked myself at 1 in the morning, the night before my interview, going, how am I going to explain this in a way that makes logical sense and mathematical sense, even if we know that it might be something else going on? Because it could be something completely different going on, but this is just one model. So what I'm going to ask you guys to do is I'm going to ask you guys to do what I did, but without using a calculator or your phone. I'm going to ask you guys to have a think about what kind of approximations could you make to work out the sum of 2 to the power of something gives you a million. I'm not expecting you to know this. I'm not expecting you to work it out. I'm saying what assumptions and what estimations can we make to work that out. Off you go. Okay, so I'm less interested in the answer. I'm more interested in how you got there or how you attempted to get there. And I'm interested in any kind of approximations or estimations you might like to use to get yourself quite neatly and nicely to the answer to the question of 2 to the power of what? In other words, how many chromosomes would there have to be to give you 1 million? Any ideas, any suggestions? Yes?
20.
How did you get there?
2 to the power of 10 is approximately 1,000.
Okay, brilliant. Hold it there for a second. So we had a suggestion here of 2 to the power of 10 is approximately 1,000. That is actually true. I'm interested in going back a step even further. So let's come back to you in a second, once we've got to how we know, because obviously that's something you knew. How could we work out 2 to the power of 10 is approximately 1,000? By doing an even simpler approximation. And then I'll come back to get to 1 million. I'll come back to you. Even simpler approximation. Start with 2 to the power of something even simpler. In maths, a really nice number for us to start from if we're trying to get to 1 million, or if we're trying to get up to 1 billion or 1,000 or 10,000, is the number of 10. So if we can find an approximation of 2 to the power of something gets us close to 10, we're laughing. So, what's that? Anyone? Any ideas? Give me 2 to the power of something that gives us close to 10. Right, okay. So let's start with 2 to the power of 3. 2 to the power of 3 is 8. So what could you could you approximate? 2 to the power of what would give you 10? Yeah, okay, so 3.5. So we know 2 to the power of 3 is 8. We know 2 to the power of 4 is 16. That's much too big. So let's say 2 to the power of 3.5 is probably a bit big. So let's round it 3 and a little bit. 2 to the power of 3 and a little bit would give us 10. Now, what's really nice is if we want to get to 1,000, we know that 1,000 is 10 cubed. So if we take 2 to the power of 3 and a little bit to the 3, because that bit was the 10, are you with me? What will that give us that's nice and neat? What's the law for how we do a power to a power? We times them. So what's 3 and a little bit times 3 if we want a nice round number? 3 times 3 is 9. 3 and a little bit times 3 is 10. Do you see how we've now approximated something really nice and simple to give us 2 to the power of 10 is about 1,000, which is what the gentleman down here said. 2 to the power of 10 is actually, do you know what it actually is? 1,024. But if you didn't know that, you could use the approximation of 2 to the power of 3 equals 8 to give you, working up, that 2 to the power of 10 is about 1,000. Now that we've got 1,000, how do we get to 1 million from 1,000? What's that? 1,000 times 1,000, in other words, we square it. 1,000 squared is 1 million. So, if 2 to the 10 is roughly 1,000, 1 million is roughly 2 to the 10 to the 2, which is therefore 2 to the 20, because you times it, which is what this gentleman said here said. Excellent, well done. So what we have approximated, now I know in this day and age we always use calculators for everything, but it's really useful to be able to make approximations like this to try and get to answers that would take us a lot more computing power to use our calculators for. So we've approximated that 2 to the power of 20 is about 1 million. In fact, the answer for 2 to the 20 is actually just over 1 million, but it's pretty close, relatively speaking. So what this tells us is that if my model were true, the thing about the chromosomes, if it were true, then it would take roughly, well not roughly, but because you can't have half a chromosome, but it would approximate to 20 different chromosomes, each of which carried one white version of the gene colour allele, and therefore it would give this black mother a 1 in 1 million chance of passing on all 20 versions of the white allele to her baby in order to make a white baby. Make sense? This was the logic that I employed. It sounds a bit bonkers, but that's what I actually thought. Well, I have to explain it somehow. So this is what I went on to say in the programme.
Well, the doctors that spoke to this amazing situation said that it was a 1 in a million chance. Now, there is one explanation that could explain why that would be. If we look at normal inheritance of, say, eye colour that you might have learned about at school, it's one gene that controls that, and you have 2 versions of that gene, one from your own mother, one from your own father. There's a 50-50 chance that when you have a baby, you'll give them either, let's say, the brown version or the blue version, and that will ascertain which colour they get as their own eye colour. Now, skin colour is actually controlled by up to 20 different genes. Thank you.
Oh, the baby's a there's batteries in there, and off he goes.
So the colour that your eyes will end up, if you have a brown and a blue version, you'll end up with brown eyes because brown is what's called dominant, so it wins. So in that situation, you're
One in a million.
Right.
With colour,
So that's
the dominant gene, is it?
Exactly, but when we look at skin tone, if we apply that to then 20 different genes, rather than just one, each of which has a small effect on colour, you have almost infinite combinations of different colours from two different
Does
coloured
that mean
parents.
Richard, as a father there, he is a very dominant donor
It's
there?
totally by chance. Can you imagine it? Like you've got 20 pairs of playing cards, one black and one white, and it's the chance of picking the white version of all of those 20 pairs if you randomly pick one from each pair. So it is possible, but that becomes 1 in 2 times 1 in 2 times 1 in 2. So it is 1 in 1.
So it's really embarrassing for me to show you that because you can see how completely awkward and uncomfortable it is. It was one of those clips where I just thought, I hope nobody ever sees this. And now I'm going out there showing it to all of you guys and saying, hey, learn from my mistakes. But the fact is, as you can see, all they were interested in was hearing, oh, but it's 1 in a million, right? Oh, right, it's 1 in a million, yeah. And I'm like, oh, well, maybe. And I go on later in the clip, which just gets more awkward and more embarrassing, which I'm not going to show you, to then try and say, well, actually, we don't really know, and we need her to have more babies and to have any kind of clue as to what's going on, so it's a proper science experiment. By the way, she did have another baby this year, which by this logic would mean that she had a 1 in a million chance again of having a white baby. What colour do you think the baby was? It was white. So clearly, this isn't true at all. There was obviously something completely different going on. She probably had a dominant mutation, which meant that all her babies will now be white. But the point is, don't trust everything you read in the newspapers. Look out for when the media might be intentionally, in this case, abusing statistics to sell a good story when there might be other explanations that clearly just don't sound so cool. Don't be caught out like I was. So my final embarrassing moment number 3, is when I was invited on the I spent a season as a resident science expert on an afternoon show on ITV called the Alan Titchmarsh Show. The Alan Titchmarsh Show, I had a slot explaining science news stories similarly to how I did on this programme. So I'm going to show you one more clip, and I'd like you to be thinking again why this was my 3rd most embarrassing moment.
Right, Bill from Gosport, is it true that cats don't like to be stroked? Is purring a salamander?
Now this is very interesting because I know lots of cats who seem to be like to be stroked, but a study was done where they looked at the stress hormones of cats and they found that although some of them do like the odd tickle, none of them actually enjoyed sort of sustained periods of stroking. And in fact their stress hormones rose. Even if they tolerated the stroking, they got more stressed.
Now, did you see my cat Spud?
I think we want to know about his cat Spud. Now, turn to a friend. Why was this an embarrassing moment for me? Okay, any thoughts? Any thoughts? Any suggestions? Any ideas? Anyone? Yes. Great suggestion. Maybe the cats were stressed because they were being tested. Now, this was actually a very good study, the one that they carried out. Again, it was published in the Mail, which not necessarily the most believable journal. However, if you go back to the original study, the actual results of the study, it was done at the University of Lincoln, and it was a very good bona fide study. They did control it, which is what you're talking about, to make sure that it wasn't just that they were more stressed because of the study. They did it on a large number of cats. They used adequate, like I said, control measures. It was a very good study. The conclusion of the study was that, yes, on average, if you stroke a cat, it will get more stressed. Now, there's a clue there in what I just said. but as to why this actually, the conclusion that I drew in the programme, as has been drawn on the newspaper, which is that if you stroke your cat, it will get more stressed, doesn't necessarily correlate with the conclusion of the study, which was that on average the cats got more stressed. Let's see where I'm going with this. In order to understand this, I'm going to draw us what I've labelled a cat function. So in my cat function, I'm going to plot stress level across the bottom, and I'm going to plot number of cats up the side, up the y-axis. Okay, so if I was to draw a graph, they're not being petted at the moment, they're not being stroked, this is just the average stress levels of cats. What would a graph of stress level and number of cats roughly look like, do you think? Straight line, a random, a curve? Any ideas? Any suggestions? Come on. Going up, going down, flat, up and down. I can see lots of these, lots of these. So I can see a few of these. Okay, anyone familiar with this shape? Anyone know what this shape is called? Yeah? What's that? It's a bell curve, and specifically, this is what we call a normal distribution. The actual equation for it is this, if anyone's interested, you don't need to know this. But what this represents is the fact that some cats would be pretty chilled out, on average. Some cats would be super stressed, on average. But most of them would be somewhere in the middle. Kind of like if I asked you to plot a graph of the heights of people in this room. Some of you would be pretty small like me, some of you would be quite tall, most of you would be kind of average. It's a bell curve, it's a normal distribution. The middle, or the sort of midpoint, or what we call the average, is called the mean. There's various different types of average, but on this one I've labelled the mean. Anyone know the symbol for mean? What's it called? Shout out. I heard it. Mew. Like cats mew, no? I thought it was quite cool. Anyway, so what the study concluded was that when the cats were stroked, on average, the stress level increased. In other words, the mean shifted to the right. What I, along with all the newspapers, wrongly concluded was that that meant that all of the cats got slightly more stressed. However, could there be another explanation? 30 seconds, your final 30 seconds, have a think. What could be the other explanation? Okay, any ideas? Yes. Spot on. Some of the cats got really, really stressed and skewed the average. In other words, most of the cats did indeed get less stressed, which is of course what we would expect when stroking a cat, but because some of them who hated being stroked so much, they tolerated it and got super, super stressed, and that's what we call skewed the average. It gave us what we call a bimodal, a two-humped distribution, where we've got a little hump to the right, most of them hump to the left, but still on average, the stress level would have increased. What would we do better of in terms of using an average? Instead of using a mean, what could we have used which would have helped us to see what was really going on? The mode, because the mode would have showed us that most of them got less stressed. But some of them got super, super stressed, kind of like this cat here. Okay, so what this tells us is that if we go back to the original study, we did indeed see that a week later what was published was, please don't misinterpret this study. They said, don't worry about stroking your cats. This study has been misinterpreted. On average, the stress level did go up, but most of them, of the 120 that were tested, most of them did enjoy being stroked. A few of them disliked it so much, but they tolerated it, and they got super stressed, and it skewed the average. This is exactly what was going on. By the way, I don't know where the other 18 cats went. If anyone's done a quick maths on this, goodness knows it doesn't actually add up, but there we go. So, moral of this story is, final story of the day, look out for when statistics might have been misinterpreted by the press or even by yourselves. Go back to the original study and check what it actually showed and whether the conclusion is in line with the actual data, because it may not be. So, don't believe everything you read in the newspapers. Go and check, look out for statistical fallacies, look out for intentional misuse, look out for spinning of good stories, and look out for where things have been misinterpreted. So, I've been Dr Emily Grossman, thank you very much. If you're interested in anything else that I do, please come and talk to me in the break, and I've got pieces of paper where you can leave your details. We've got a few minutes in case anyone wants to ask any questions.
Thank you, Emily. So I'm going to ask the next speaker to come and set up. While that's happening, Emily is here to answer questions about left-handed white cats and their No, it's not going there. Okay. If you have a question for Emily, now is your chance to put your hand up and ask her. I will run over with the microphone if you are close enough. So there is a question down here. I'm just checking out for any other questions available. Okay, I'm going to go down here. So I just need some quiet so everyone can hear this gentleman.
When you realised you made these mistakes on TV, did you write to wherever you were filming or?
Very good question. Very, very good question. The question was, when I realised, yeah, you heard the question. So what actually happened is this, is that the first big one was the left-handed one, right? And I got an email, in fact, my agent got an email, the day after the programme was broadcast. She got a couple of emails, one of which was slightly rude, let's say, who was kind of a bit attacking, saying, oh, stupid, you got this wrong. The other was from a professor of statistics. And he said, are you aware that this is a statistical fallacy and that actually this is not actually true, and here's some information about it. And my agent said, she was trying to protect me, she said, okay, ignore it, you've made a mistake, it's not your fault, don't worry about it. And I said, no, I want to address this. So I wrote back to this professor and I said, that's really interesting, thank you, can you tell me more? I want to understand more. He pointed me towards Chris McManus, who wrote the book Right Hand, Left Hand, which I showed you. I went to talk to him. He said to me, gosh, don't worry about this. This is such a common mistake that people make, but yes, it's very interesting. Off the back of that conversation with the professor of statistics, he invited me to come and give a talk on statistical fallacies and how the media and people like me can get caught out, which is what birthed this talk, which I'm giving to you today. So the moral of that story for me was, yes, admit when you make mistakes. It's okay to say that you've got stuff wrong, and the best thing is to then go public and talk about it and use it as an example of how we can use our mistakes to actually learn and do things differently. The other two, I didn't have an opportunity to actually correct the mistake, but it was alerted to me. And the one on the TV, the black woman one, I did go on in the interview to say, actually, we don't actually know, and it could be whole many other possibilities of what's going on in the genes, and we'd need to get the baby genetically tested. But yes, admit your mistakes and learn from them and use them as an opportunity to educate yourself and to educate other people.
Emily Grossman, ladies and gentlemen, round of applause.
If anyone's interested in knowing more or in talking to me about the work I do in schools and the talks I do, I'll be around in the break, and there's pieces of paper down here and cards if you want to take my contact details, if you want to leave your email addresses, teachers, that'd be cool. Thank you.
Thank you, Emily. So we have one more session.